I want to talk about the rank of a matrix, but first we need to know some parts of a matrix. We want to know the row space and column space of a matrix. Well, it's pretty straightforward. The row space of a matrix is the space spanned by the rows of a matrix. The column space of a matrix is the space spanned by the columns of the matrix. Technically, we should be using row vectors when we talk about row space and column vectors when we're talking about column space. And I'll do that so we don't get confused. But if there's no ambiguity, I tend to stick with column vectors because they just look better, in my opinion. So here's a average Joe matrix with 3 rows and 3 columns. The row space is the span of the rows. Just copy the rows down. And the column space is the span of the columns. Are these a basis? Don't know. We need to figure that out. But we definitely know that the span of the rows and the columns. So let's look at this. Once a matrix is put in row reduced echelon form, the non-zero rows with the pivots are the basis for the row space. What's that mean? So I put this in row reduced echelon form. I've got 2 rows that have pivots, so the first row and the second row form a basis for the row space. You can also go back to the original and take the first 2 rows. This is the only one. It's not true of the column space that you can take something from what got spit out. But since we were actually futzing with rows here, these are legitimate coefficients. We were actually playing with the vectors themselves. It's okay for the basis to be the rows in what got spit out. Or it could be the rows from the original. Either way. And the columns, though, you must go back to the original matrix. The columns in the original matrix are with the pivots. Let me just write it here. These 2 columns, column 1, column 2, both have pivots. So I go back to the original one, column 2, are a basis for the column space. Another thing we might want to do is look at the transpose. Here's my matrix. Here's the transpose of it. We flipped it along the diagonal. Now rows are columns and columns and rows, if we weren't confused enough already. What can I do with this? Well, I can just put it in row reduced echelon form and find the row space of A transpose and the column space of A transpose. But the row space of A is the column space of A transpose, and the column space of A is the row space of A transpose. Let's just move on and not do transpose stuff right now. I mean, we can find it with the A. We don't need to transpose it and really mess with our heads. So here we have a huge matrix. I'm going to find a basis for the row space and a basis for the column space. I have 3 pivots here, so I can see that a basis for the column space will be the first 3 columns in my original matrix. I also notice that the first 3 rows have pivots. I could use the first 3 rows of what got spit out, or I could use the first 3 rows of the original. But Megan, why didn't you use the rows and what got spit out? Because I didn't want to deal with the LaTeX of doing the fractions. They're a pain in the ass. So I just took the rows in the original one. The rank. Well, the column rank is the dimension of the column space. The column rank is the number of pivots. The row rank is the dimension of the row space. Well, we found the rows by looking at the rows with pivots. Well, rows with pivots, columns with pivots. We're just looking at the number of pivots. Row rank equals column rank, so we just call it the rank of the matrix. One thing we want to think about is a matrix as a function. 1, 2, 3, 4. It's got 4 columns, so I'm going to go from R4, so 1, 2, 3, 4, and I will spit out, there's 5 rows, so I'll go to R5. Sorry. My domain, therefore, is R4. My range is somewhere in R5. We don't know if it's onto. Actually, we do. Is this onto? No. 4 is not big enough to cover 5, because 5 is too big, so there's no way this is going to be onto. We've got a function from R4 to R5. The range is actually the column space. If you think about it, we're doing all possible linear combinations of the columns when you multiply it. The range is the column space. Another part we are interested in is the null space. The null space is all the stuff in the domain that gets mapped to 0. So we're solving this equation. And if I put it in row reduced echelon form, I see the null space is going to be one-dimensional because we only have this one column with a free variable. So if I want to find the basis for the null space, I'll just do the solution. find the vector that solves that equation, and I'll get 0, -3, 3, 2. The dimension of the null space is 1, so we say the nullity of the matrix is 1. Next one. Okay, let's try another one. We have a 3 by 5. I see 3, so the rank is 3, 1, 2, 3, and the nullity, because there's 2 of these, will be 2. Column space basis, I just take the first 3 columns. The nullity basis, well, I do that using these. I've got 2 free variables. I'll make this S and this T, and I can do my little thing where I solve for them, and I'll get the null space basis are these 2 vectors. Notice something interesting. Because these are at the end, it makes this much easier to see. But 1, -2, 3, -1, 2, and then 1, 0. And over here I'm going to have 0, 1. This is the S's, these are the T's. Here I have -2, 0, -1. I can just look at those columns and figure out what the null space basis is. The range is the column space. The null space is a subset of the domain. It's all the crap in the domain that gets mapped to 0. Columns with pivots, it tells me the rank of the column space. Columns without pivots result in the null space vectors. So the number of vectors equals the nullity. So if I'm looking at all the columns that either give me pivots or don't give me pivots, that means nullity plus rank equals the number of columns. That's what I wanted to talk about. Enjoy. Bye.